We're going to go through 3 Type 1 projectile problems as examples. These are actually found on page 150 of your textbook, but I have them all printed in this video, so you don't need to look them up if you don't have your book with you. Please do take notes, follow along as we're going through these problems, and I will prompt you to enter some calculations. Okay, so this first one. A stone is thrown horizontally at a speed of 5 meters per second from the top of a cliff that is 78.4 meters high. How long does it take the stone to reach the bottom of the cliff? How far from the base of the cliff does the stone hit the ground? And what are the horizontal and vertical components of the stone's velocity just before it hits the ground? I have my toolbox here so that we can find equations that we need to use. So let's start by drawing a quick picture of what's going on in here. So we've got the cliff and an object on the cliff. It gets thrown horizontally. Okay. Now we know that this would be the vertical position. We know that that is 78.4 meters high. Okay, we also know that the speed horizontally is 5 meters per second. So now that we have the picture drawn, we can list all of our given information. So let me do my x direction and my y direction. So x, I'm going to do in red, and then my y over here. So on the x side, I know I'm going to have my change in horizontal position, I'm going to have my velocity, and I'm going to have my change in time. On the y side, I've got my change in vertical position, I've got acceleration, I've got change in time, which is the same on both sides, and then I have my initial velocity in the y direction and my final velocity in the y direction. Okay, so filling in this information, the things that I do know are that my change in vertical position is going to be 78.4 meters, and I also know that that is in the negative direction, that it's going downward. I know that the acceleration due to gravity is negative 9.8 meters per second squared. And I know that my initial velocity in the y direction is 0 meters per second. On the x side, I only have one piece of given information. All I know is that my velocity is 5 meters per second. 5 meters per second, sorry about that. Okay, the things that I really want to know from the problem: A, how long does it take to reach the bottom of the cliff? So that's going to be time. B, how far from the base of the cliff is the stone thrown? That's referring to this distance, which is often called range. Change in x, often called range. And we also finally want to know the horizontal and vertical components of the stone's velocity just before it hits the ground. So thinking about when the object gets right here, it's got some final velocity, and it will still have that component of its velocity acting in the horizontal direction, acting in the x direction. That is still going to be 5 meters per second, because we know that it's not accelerating in the x direction at all. So the only thing that we actually need to calculate is our final velocity in the y direction. Okay, now that we've got all this information here, I'm going to just shrink it down real quick. So I kind of rewrote it a little bit to make it a little bit neater. Anyway, the next thing that we need to do is actually calculate our A. So we have more information. We have 3 pieces of information on the y side, and so that is enough information to calculate our other two missing pieces of information given our DAT VV, or in this case our WAT VV. YAT VV, perhaps? Anyway. We're going to use an equation to calculate time. So looking at your toolbox, with the given information that we have, remember that change in y is representing our change in vertical position. So this is kind of like saying delta D. So when you're thinking about this, this represents D in the y direction, this represents D in the x direction. And instead of writing dy and dx all the time, sometimes I just write them like this because it's just less shorthand to have to write, less subscripts to keep track of. So we're gonna use this second equation here because it has our change in position, vertical position, it has acceleration, and it has initial velocity, and we're looking for time. So this is the equation that we need to use. So I'm going to go with, here's part A, delta D is equal to 1/2 times acceleration times time squared plus v initial t. And I need to solve this for t. First thing I know is that since initial velocity is 0 meters per second, that means this whole term is going to be 0. So then I am left with change in position is equal to 1/2 times acceleration times time squared, and I need to solve for t. So I can multiply both sides by 2 and divide both sides by a, and then take the square root. So t is going to be 2 times change in position over a, and then the square root of that whole thing. Now I can fill in my missing information. So that's going to be the square root of 2 times negative 78.4 meters divided by negative 9.8. And then I can just calculate that and get my answer. When you calculate that, you should get 4 seconds, or 4.0 seconds, because we have two numbers given in our problem, 5.0 and 78.4. The 5.0 has 2 sig figs, 78.4 has 3 sig figs. I'm going to go with the fewer number of sig figs, so 2. So 4.0 is my final answer for part A. Okay, now let's start looking at B. How far from the base of the cliff does the stone hit the ground? Well, now I can use my answer to part A, that time is 4 seconds on both sides. Whenever you're doing a projectile problem, time is the connecting factor between the x and the y side. So you've got to always figure out time first. Okay, if that is an option. Sometimes you need to go through another step to get to time. Anyway, in this case, that's exactly what we did. So now we can calculate how far from the base, or the range, the cliff, from the base of the cliff, the stone hits the ground. So on side B, we have constant velocity, which means we're going to be dealing with equation 4. So d final is equal to v times delta d plus d initial. So delta d is equal to velocity times change in time. And so this equation is already solved for change in position, so I don't need to do any other rearranging here. I just need to plug in my information that my velocity is 5 meters per second and my time is 4 seconds. So my change in position will be 20 meters, not meters per second. And to write that with the correct sig figs, we would want 2.0 times 10 to the first meters. All right, so A, 4 seconds, B, 20 meters. Time for C. For C, we already have one of our answers down. We already know that the final velocity in the horizontal direction, the horizontal component, is still going to be 5 meters per second. You don't have to make any changes there. Well, 5.0. In the y direction, though, because this object is accelerating downward, we do need to find the new final velocity. It's not going to be 0. We're not talking about the velocity once it has hit the ground and stopped. We're talking about the velocity that it's hitting the ground with. So we need an equation that will solve for final velocity in the y direction using equations 1, 2, or 3. You could use either equation 1 or 2, and probably most convenient to just use equation 1. So v final is equal to acceleration times time plus v initial. And we know that our acceleration is negative 9.8 meters per second squared times our times time, which is 4 seconds. Initial velocity was 0, so I just need to multiply those and find my final answer, which is negative 39.2 meters per second, or with just 2 sig figs, negative 39 meters per second. All right, and notice that my horizontal velocity is still positive. It's still going forward to the right, and my final velocity in the vertical direction is negative because it's going down. There you go. There's your first problem. Let's move on to our second